Welcome to this module on soft switching. It is arranged in two parts. In part one, which we'll cover in this module, we'll look at benefits, principles behind soft switching, and various topologies, synchronous buck rectifiers, and resonant converters. And then in part two, which we'll cover in a separate module, we'll also look at full bridge DC to DC converters and design considerations. And various sources that are used are listed here. So let's look at the objectives. What is soft switching and what are the basic principles? We'll concentrate on a few popular topologies, and we'll also look at design techniques. So in soft switching, transitions occur under favorable conditions when either device voltage or the device current is zero. And that leads to reduced switching losses, switching stresses, and possibly lower EMI, and because of lower switching losses, there's easier thermal management. And this soft switching is really a must at very high switching frequencies. Also at medium frequency at high power levels. But it involves compromises and conduction laws, switch ratings, passive components, etc. So the objective of this module here is really not to go into the device physics, which Professor Robbins covers. So here we look at a cross-section of this MOSFET, and it could be the device physics can be understood in terms of these capacitances that are shown between the drain and the source and the gate terminals. And then we have this IV characteristic where the drain current is plotted as a function of drain to source voltage. And also, in order to understand the switching characteristics, we need to know the transfer characteristics where the drain current is plotted as a function of gate to source voltage. So to obtain the switching characteristics, one can go to a circuit model as you see here, and again we will not go into the details of that, but rather we will look at from the terminal characteristics point of view. Let's take this buck converter where we have this MOSFET, and we can assume this diode to be ideal here, and the output stage of this buck converter can be represented with a current source over here. So we see that for the turn-on characteristic, the gate to source voltage is raised from 0 to some value VGG here, and so the gate to source voltage is plotted over here as a function of time, and the voltage across this FET and the current through it are plotted in here, right? So you see that when we increase the gate voltage, apply the gate power supply here, the gate to source voltage rises, and nothing happens until it reaches the threshold level, and so that represents this delay time here in the turn-on characteristic. And beyond that, then current begins to rise through the FET, but while the current is rising, and there's still some current flowing through this diode, and therefore, assuming this diode to be ideal, the voltage across the FET remains at Vin as shown here. And then only after this current through the FET reaches this output current, then the drain to source voltage is free to fall, and here we are showing linear characteristics. The current is rising in this rise time TRI, and the voltage is falling in this time TFV here. So similarly, we can look at the turn-off characteristic here, where the voltage applied to the gate is brought to 0, and again, there is a certain value of this gate to source voltage. Before falling to that level, there is this delay time TD off here, and after that, the drain to source voltage can rise. So we have seen that before, and here we can see the switching power loss in effect as the voltage and currents are changing associated with this FET. So there's every time we turn it on, there's energy lost represented by this triangular area here, and similarly when we turn it off, there is a loss of energy represented by this area here. So on an average, the switching power loss can be represented by this equation here, and which shows that it's of course proportional to the input voltage that we have and the output current and the switching frequency here. But it also depends upon the turn on time and the turn off time here. So this is the expression that we get for the switching power loss. Every time a transistor switches, we have this loss, and as you can see, at higher frequencies, this loss can be significant. So these are the problems of hard switching that we just showed, that we have switching loss, which results in device stresses, and then also this loss is in terms of heat, and so thermal management issues show up. And then, depending upon how fast we are switching this FET, we have this problem of DI/dt and dV/dt, leading to EMI, and of course there could be some energy lost in these stray inductance and capacitances here. So what are the solutions? Well, we can use Snubbers that Professor Robbins talks about in his module, and we can have a good circuit layout to reduce stray capacitances, and also we can pay attention to the gate drive circuitry, how this is laid out, and what is the turn on and turn off speed of this FET. But our concentration in this module is really on soft switching to achieve ZVS, zero voltage switching, or zero current switching. So we can see that this power loss results in loss of efficiency. So if you look at this power electronic equipment as a block here, you have input power coming in here, you have output power over here, and certain amount of power is lost, P loss here. So in terms of these three powers, we can represent the efficiency, and as you can see that input power is the sum of these two here. So writing it in terms of the output power, we can write the efficiency like this here. So what it shows is that, and then we can manipulate this equation and write the output power as a function of P loss in terms of the efficiency. And you can see that efficiency plays a great role in terms of how much power could be throughputed, can be transferred through this power electronics equipment. So if you look at, let's take P loss of 10 watt. So this curve here represents a constant power loss of 10 watts. But if you had an efficiency of 0.84, the amount of power that can be, that's the output power here, is only 50 watts here. Whereas if you increase this efficiency, let's say to 0.94 here, then the amount of power that we can get, output power, is 150 watts. So you can see that in the same package, if this thermal loss is dictating the size of the package, then you can have 3 times the output power, and therefore the power density is tripled for the same amount of loss here. So minimizing losses are very important, not in terms of the cost of wasted energy, but also in terms of the size of the package. So there are certain options we have. One is the snubber circuit, and we'd rather not use it if we don't have to. And so here the turn-on snubber that Professor Robbins talks about, very seldom used. So for the sake of completeness, I have included these here. You can look at it at your leisure. And then we have turn-on, turn-off snubbers, where you have this RDS snubber as shown here across the FET. But in these snubbers, using these snubbers, the total power loss doesn't really change. very much. Actually, it just transferred from the device to the snubber. So this, this is a solution, I would say, of last resort. So this brings us to this topic of soft switching, and there are two types of soft switching we can look at. Where one is ZVS, where the transition occurs when the voltage across the device is zero, and the other one is zero current switching, where when the switching occurs when the current through the device is zero. And so what are the advantages? Lower losses, quite often the case. So maybe it could be softened here. Lower EMI, maybe, because as you'll see here, there's no clear-cut case that can be made, but certainly in many circuits it results in low EMI, and therefore with these two, if they are achievable, then we can operate at higher frequencies, which is always the goal, to reduce the filter size. So we look at the zero current switching, where at turn off, the switch current is brought to zero before the gate voltage is removed. So it's really ideal zero current turn off, so zero loss under transition. Also at turn on, it's a low loss transition because the series inductor here acts as a snubber, lossless snubber, and but the energy in the junction capacitance of this FET is lost. So this is best suited for converters with IGBTs because IGBTs have a long tail current at turnoff, so it's better suited for that. But in this module here, we will basically concentrate on zero voltage switching, quite commonly used with MOSFET circuits. So here you see that at turn off, it's a low loss transition. So at turn off, prior to that, the current is flowing through the channel of this FET, and here the parasitic diode that comes is shown explicitly, and also the drain to source capacitance and perhaps some external capacitor is added on. They are shown explicitly over here, as you see. So before we turn this FET off, the current is flowing through the, let's say, the channel of this FET, and then as soon as we remove the gate voltage, because of this capacitor, which has essentially zero voltage here, this is a zero voltage turn off, essentially. So this parallel capacitor acts as a lossless snubber. So when we look at turn on here, then what we see here is that at turn on, under the circuit implementation, the current is flowing through the anti-parallel diode here. So as you can see that if that's the case, the switch voltage is zero, and before we apply the gate voltage, and therefore it's also it's really an ideal zero voltage turn on here. So we have to make sure that these two conditions happen simultaneously. That at turn off, the current is flowing through the channel, so you forcefully bring that to zero. At the same time, at turn on, this anti-parallel diode is conducting, and then only we turn on this FET. So this is preferred at very high frequencies using MOSFETs, which is the case in many circuits here. So you can see the switching waveforms in hard switched and zero voltage switched circuits, and you can see that we are turning this on here. So we have drain to source voltage at some level, and then the FET drain to source voltage, I hope I said that, but gate to source voltage, let's say some negative value to positive value, is rising, and as it's rising, the drain to source voltage is falling as this gate voltage is rising here. So that clearly shows that it's a hard switched condition, whereas when we go to zero voltage switched turn on here, that before the gate to source voltage rises, the drain to source voltage has already come down to 0 here. So it shows that it's source switched. So let's look at these principles and apply them to a synchronous buck converter. So we know why we use a synchronous buck converter when the output voltage is low, instead of having a diode and living with that diode voltage drop. We rather use a FET here, and we can have very low RDS on at low voltages, and therefore it results in higher efficiency. So these synchronous buck converters are used, and these are covered in the previous course, but here what we are looking at is providing zero voltage switching in this synchronous buck converter. So this zero voltage switching doesn't do anything to the voltage transfer ratio of V0 over Vn. That doesn't change, essentially remains the same. But in order to achieve this ZVS, we have to have certain circuit conditions. So what are those conditions? So let's look at this. Here is the switching signal to this to these MOSFETs here, Q plus to the top one, Q minus. The complementary signal is also shown here, and this voltage V sub A is plotted over here. So if you are using the synchronous buck converter without zero voltage switching, this IL waveform is shown by means of this solid lines here. Okay, and you can see that the average of this IL curve is the average is the current that is through this inductor, which then is supplied to the load, because the average current through this capacitor is 0, right? So now if we want to achieve zero voltage switching, what we have to do is to make this inductance value small enough that the current that flows through it is both positive and is also negative at the transition instance over here. And we have to make sure that there is a delay time here between the turning off of the upper transistor and turning on of the lower transistor here. So that is shown by these two plots over here, and we will apply this to the circuit that is shown over here. So let's analyze this here, and let's look at the turn off of this upper transistor and turn on of the lower transistor. That means we are looking at this value at the peak value of this current IL, which is shown over here. And during this transition interval, we can assume this current to be constant at its peak value. And so we are really looking at this transition during this delay time where the upper transistor is turned off and the lower transistor is turned on here. Okay, so that delay time that I talked about. So what happens is that during this delay time, both the signals are 0 to the upper transistor and to the lower transistor. So what we see here is that in this case, you have two capacitances, and let's assume these two capacitances to be equal as C, value of C over here, and you can see that this current IL hat is then going to split equally between these two capacitors, assuming them to be equal. So how does that come about? Well, let's look at first this equation here. This is nothing but Kirchhoff's voltage law, where the voltage across the top capacitor and the bottom capacitor here, VC plus and VC minus, they two add up to the input voltage. So that's Faraday's voltage law. And if you take the derivative of the equation above with respect to time and multiply that with C, the capacitance, we get this equation. Remember that this Vn is constant, so its derivative is 0. So you can see that this quantity here, this term is the current that is through the top capacitor, and this here is the current through the bottom capacitor here. So the sum of these two currents is equal to 0, and therefore one is the negative of the other based on the directions that these are shown here. And so these two equations then together tell us that the output current IL hat splits equally between these two capacitors. So it's we can see that it's going to be charging the top capacitor, and it will be discharging the bottom capacitor here. So we'll take a look at this. So we have taken a look at that, and so we have to ensure that you have sufficient delay time so that the top capacitor gets, going back to this here, the top capacitor gets charged, which is being turned off, and the bottom capacitor is discharged, which was initially equal to the input voltage, and it goes to 0, but it cannot go negative because there is an anti-parallel diode, and so the voltage across this bottom capacitor cannot go to cannot go negative, so the current begins to flow. This current, all the current begins to flow through this anti-parallel diode, and this current goes to 0. So this is out of the picture here, and then when this signal comes on to the bottom transistor, then rather than flow through the diode, this current then flows through this lower MOSFET in this direction here. So that's, we have achieved a 0 voltage turn off of the upper transistor, and we have achieved a 0 voltage turn on of the bottom transistor, and at this instant of time, when the current through the inductor is at its peak. But we also have to make sure that the same thing happens when we turn off the bottom transistor and turn on the upper transistor. So that happens at this instant of time when the current is negative through this inductor and had some value IL mean here. So we have to make sure that you have enough delay time to make these voltage transitions across these two capacitors happen. So you can see here that at IL hat, which is the peak positive value, the amount of delay time should be greater than what you see here, because you have these two capacitors each equal to C, and this current IL hat is splitting between the two, so you can easily see that the delay time has to be greater than what you see on the right hand side here. But so the minimum delay time when we are turning off the bottom transistor, then we have only IL minimum to deal with, okay? Because that's the current we have through the inductor, which makes these voltage transitions happen. And so you can see that we get this expression, but usually this IL minimum, in absolute value is much lower than IL peak. So the amount of delay time we get from this expression here is larger than what we get over here. So generally, we take the larger of the two and use that as the delay time for both these transitions. Okay. So, but we have to make sure that the current to the inductor goes both positive and negative in the same switching time period. So that's kind of a disadvantage of this, that achieving this soft switching is that you have larger current ripple through the inductor, which then flows through the output capacitor here. So we can model this in PSpice, and if you look at the laboratory we have developed along with this first power electronics course, there is an experiment which our simulation that talks about this here. And the waveforms you can see here that we have the two gate voltages in green and red, and then what is happening to the current to the inductor. So one of the transition is happening at the peak of the inductor current, positive peak, and the other transition is happening at the peak of the negative inductor current. So we have looked at soft switching in synchronous buck DC-DC converters, but there are other circuits where we can have soft switching as well, and one of them involves series resonant converters. But we will basically look at series resonant converter circuits, and we'll start with concepts. So let's look at this RLC circuit shown, and let's analyze it in sinusoidal steady state. And we can plot this impedance looking from the terminals here as a function of switching, as a function of frequency. And we see that at omega naught, which is a resonant frequency, this has the minimum impedance where the capacitive resonance reactance, I should say, cancels out the inductive reactance. And we can plot a family of characteristics for different values of Q, which is defined. So we can see that at frequencies below the resonant frequency omega naught, in this region, the capacitive reactance is higher than the inductive reactance, and therefore this circuit looks capacitive, and therefore the current is leading the voltage. And whereas in this region, where the switching frequency, the frequencies we're dealing with are higher than the resonant frequency, then the inductive reactance dominates. This circuit from the terminals looks inductive, and therefore the current is lagging the voltage. All right, so let's put this RLC circuit into a half bridge as shown over here. And first we'll look at operation at switching frequencies below the resonant frequency. And you can see that as we turn these transistors on and off, this voltage, which is called VAB, it goes from minus VD over 2 to plus VD over 2. So this is the, and we also see that the current here, this is being at frequencies below the resonant frequency. This circuit is capacitive, and therefore this current is leading the voltage. So what we see here is that at this instant of time, we are going to turn off the lower transistor, and we are going to turn off the upper transistor after a short delay time. And during that delay time, this current being positive, this current has shifted to this diode, which is shown explicitly here, D minus. So at that time, we are turning on this upper transistor at this instant of time, and that is very much like hard switching. And so the voltage across the transistor that we are turning on is equal to the input voltage, and as soon as we turn on this transistor, the current will shift from D minus to T plus, and so we also have to deal with the reverse recovery characteristic of this diode. So it's very much like hard switching, and that's a very serious disadvantage of operating it at below the resonance frequency. But we see that for turning off of this upper transistor, things are much better, because at that time we are turning off the upper transistor at this instant of time, and the current has shifted to D plus, because this current is negative in this region, as you can see. So this current, negative current, is flowing through D plus, and therefore the voltage across this transistor is 0 at that time, and therefore we are turning off of this. We are turning it off when the current is 0 already. So that is not a problem, and the same thing happens in the other half cycle. So let's move on to operation at above the resonant frequency. So in this case, the circuit, RLC circuit, is inductive, and therefore this current is lagging behind the voltage. And you see here that we are turning off the lower transistor here, T minus, and at that time the current is negative, so it's really flowing through this transistor. but we have this lossless snubber capacitor. So it's really a 0 voltage turn off for T minus, and then when we turn this transistor off, this current being negative, this current is flowing through D plus as shown here, and only after it's flowing through this anti-parallel diode or flowing in the reverse direction that we apply a gate pulse to this upper transistor, and so it's turning on at 0 voltage. So we essentially get a 0 voltage turn off because of these lossless snubbers, and we can afford to put these capacitive snubbers here because we see that turn on occurs at 0 voltage as well. So this is a circuit which is quite commonly used in various applications. One of them is ballasts of compact fluorescent lamps. So bringing to the close here, in this module we have seen reasons for soft switching, we have seen the basic principles, we have applied it to synchronous buck converters, and also we have looked at resonant converters. So thank you very much.